Welcome to the Deep Dive. We're diving into something pretty fundamental today, like the building blocks of everything you see and touch, even you and me, atoms. We all learned about these back in school, right? But the thing is, the way we picture and understand atoms has, changed a lot over time.
Yeah, it's really amazing how much our understanding has evolved over time. And
Hmm.
knowing about atoms, it tells you so much about, how everything works at the most basic level.
Right. So in our deep dive today, think of it like uh, our mission is to really unpack the structure of the atom. And we're not going to just list off the protons, neutrons, and electrons. We're going way deeper than that. We want you to really grasp how they're arranged, how they act, and how this microscopic architecture determines all the properties of the matter that we see and interact with every day.
Yeah, and we have a ton of sources, all kinds of stuff to really get into the weeds with this.
Perfect. So, uh, where do we even start with something as complex as the atom?
Oh,
Maybe by tracing how our understanding of it has changed over time.
yeah, definitely. I think that's a really good place to start because it's easy to just take our current understanding for granted, but it took centuries of really clever people doing some seriously smart science to get where we are today.
Yeah.
And it all started really with this idea of atoms being these solid, indivisible particles, the smallest possible bits of matter, thanks to Dalton.
Yeah, like tiny little marbles you can't break. So that was the initial thought. But then didn't Rutherford come along and completely change that view?
Yeah, he totally did with his gold foil experiment. That was a big deal
Yeah.
because, he discovered that the atom is mostly empty space with this super tiny, super dense nucleus at the center, and it's positively charged. And that nucleus, it's surrounded by electrons. So yeah, that was a huge shift in thinking from the idea of a solid, impenetrable atom.
Yeah, it's kind of mind-blowing to think about how much empty space there is in everything. So then we had this idea, of a miniature solar system. But it didn't stop there, right? Bohr came in and made it even more, I don't know, complex.
Yeah, Bohr, he brought in this crucial idea that the electrons, they don't just orbit randomly, they orbit in specific energy levels, like fixed orbits, almost like, rungs on a ladder. And what he said was that electrons could only exist in these specific energy levels, and that energy was absorbed or emitted when an electron jumped between levels. And this explains why, excited atoms emit light in very specific colors.
Oh, so that's why we get those emission spectrums? That makes sense. So, okay,
Yeah.
electrons aren't just randomly buzzing around there in these specific zones.
Mm.
But then the modern view, it kind of moves away from that neat orbit picture, doesn't it?
Yeah, it does. The quantum mechanical model, it's a huge leap forward from those fixed paths. So now instead of orbits, we have these things called orbitals, and they're like regions of probability. It's like a fuzzy map around the nucleus that tells you where the electron is most likely to be found.
So it's not like a defined path. It's more there's a chance the electron's here, a chance it's there. That must be super hard to wrap your head around.
Hmm.
And wasn't that partly thanks to, what was it, Heisenberg's uncertainty principle?
Yeah, the uncertainty principle. It basically says that there's a limit to how precisely you can know both the position and momentum of an electron at the same time. The more you know about one, the less you know about the other. And it's this inherent fuzziness at the quantum level means we can't actually predict the exact path of an electron.
Wow. Okay, so ditch the perfect trajectory idea.
Yeah.
It's all about probabilities now. And that's where Schrodinger's equation comes in, right?
Right, exactly. Schrodinger's equation, it's like a mathematical description of the wave-like behavior of electrons. Think of it like a weather forecast. They don't tell you exactly where every raindrop will fall, but they give you the probability of rain in a certain area. And Schrodinger's equation, it gives you the shapes and energy levels of these orbitals, the areas where it's most likely to find an electron.
So a probability map of where these electrons might hang out.
Yeah.
And then there's this idea of electron clouds to visualize them.
Right. It's a really good analogy. So instead of picturing a sharp, defined orbit, imagine a fuzzy 3D cloud around the nucleus. The denser the cloud, the higher the probability of finding an electron there.
Okay, so we've gone from solid spheres to empty space with a nucleus, then to fixed orbits, and now probability clouds. That's a lot. Maybe we can just recap the main points of each of these models so far.
Yeah, totally. Just so you remember, Dalton gave us the solid, indivisible atom. Then Rutherford showed us that it's mostly empty space with a dense nucleus at the center. Then Bohr, he brought in the idea of those specific energy levels or orbits. And finally, the quantum mechanical model, which describes electrons existing in these probability regions, orbitals, It's been a journey.
It definitely has. All
Uh,
right, so let's zoom in now on like what those atoms are actually made of. Those subatomic particles, the super tiny bits.
yeah, let's break it down. So we're talking about protons, neutrons, and electrons, the fundamental ingredients.
So protons first. They're found in the nucleus, the atom's core, and they have a positive charge, right?
That's right, positive one charge, and they have a mass of about 1 atomic mass unit, or a mu. But they do more than just bring positive charge. They're pretty important for, like, the identity of an atom.
Yeah, because the number of protons determines the atomic number, and that defines what element it is, right? Like, change the number of protons, you change the whole element.
Yeah. Exactly. If you have 1 proton, you've got hydrogen. 2 protons, helium. It's like their unique ID.
Okay, so protons are like the element's fingerprint. What about neutrons? They hang out in the nucleus too, but they're neutral, no charge. And they have roughly the same mass as a proton, right? What's their main job in the atom?
Well, they're really important for keeping the nucleus stable. Remember, all those protons in there are positively charged and like charges repel. So neutrons act like a buffer. They kind of counteract that repulsion and hold the nucleus together.
They're like the peacekeepers.
Mm.
And they also play a role in isotopes, right? Like those versions of an element that have different numbers of neutrons.
Exactly. Isotopes are atoms of the same element, so they have the same number of protons, but they differ in the number of neutrons, and that gives them different mass numbers. Like carbon, for instance. Carbon-12, it has 6 protons and 6 neutrons, so it has a mass number of 12. But carbon-14, it still has 6 protons, but it has 8 neutrons, giving it a mass number of 14. Same element, different weight.
All right, so protons tell you what element it is. Neutrons determine the isotope. Got it. Now for the electrons, those tiny negatively charged particles that are like zooming around outside the nucleus.
Right, they have a -1 charge, and their mass is so small compared to protons and neutrons. They exist in those orbitals we talked about, those probability regions around the nucleus. That's what we call the electron cloud.
And even though they're light in terms of mass, they have a huge impact on how an atom behaves chemically, right? They determine how atoms interact with each other and form bonds.
Yeah, definitely. Whether it's sharing electrons in a covalent bond or transferring electrons in an ionic bond, the way those electrons interact is what makes an atom chemically unique.
Okay, so we have this dense nucleus packed with positive protons and neutral neutrons, somehow staying together despite like wanting to repel each other. And then we have these tiny electrons whizzing around in their probability clouds, interacting with other atoms. It's a pretty amazing setup when you think about it.
It really is. It's all a balance of these fundamental forces. The positive charge of the protons attracting the negative charge of the electrons, that's what holds the atom together. And of course, neutrons are key for keeping the nucleus stable in the first place.
It's amazing how everything is balanced out. So we've mentioned atomic number and mass number, but can you just like lay out what those actually mean again?
Sure. The atomic number, it's simply the number of protons in the nucleus of an atom. That's what gives each element its unique identity. Hydrogen has an atomic number of 1, oxygen has an atomic number of 8, and so on. It's like their fingerprint.
And the mass number, that's the total count of protons and neutrons in the nucleus, right?
Yeah.
That helps you distinguish between different isotopes.
Right, like we talked about with carbon. Carbon-12 has an atomic number of 6 because it has 6 protons, and a mass number of 12 because it has 6 protons plus 6 neutrons. For carbon-14, the atomic number is still 6 because it's still carbon, but the mass number is 14 because of the 6 protons plus the 8 neutrons.
That makes total sense. All right, so we've talked about the particles in the nucleus, but those electrons, they aren't just randomly floating around in that electron cloud, are they? There's a specific order, right? Like with electron configurations and orbitals.
Yeah. Electrons are arranged in specific orbitals around the nucleus, and each of those orbitals has a specific shape and a specific energy level. So think of it like shells surrounding the nucleus, and within those shells you have subshells, and then in those subshells you have the actual orbitals.
Kind of like those Russian nesting dolls.
And then there are different types of orbitals, like s, p, and d orbitals, each with their own shape. What do those look like?
Yeah, so an s orbital, it's like a sphere centered on the nucleus, just like a round ball. A p orbital, it's shaped like a dumbbell, and there are 3 of them, one for each of the x, y, and z axes. And then the d orbitals, they get a little more complicated. They have these cloverleaf shapes, and there are 5 of them.
That's hard to imagine. And then there's the electron configuration. That's like the address of each electron, telling you exactly what orbital it's in, right? Right, it tells you where the electrons are hanging out. Like if we take carbon, it has 6 electrons. Its electron configuration is 1 high bus 2s into 2p injures. What that means is there are 2 electrons in the 1's orbital, which is the lowest energy level, and then 2 electrons in the 2's orbital, the next energy level up, and finally 2 electrons in the 2p orbitals, also in that second energy level but a different subshell.
So that tiny little configuration tells you so much information. It's this arrangement of electrons that's really important because it explains those periodic trends, those repeating patterns we see on the periodic table, right?
Exactly. The periodic table isn't just a random arrangement of elements. Elements with similar outer electron configurations, they end up in the same vertical column, a group. And because they have similar outer electron arrangements, they behave in similar ways. It's pretty neat.
So let's talk about some of those trends. What about ionization energy? Can you explain that?
Sure, ionization energy is basically the energy you need to remove an electron from a neutral atom that's in a gaseous state. So if you look at the periodic table as you move across a period from left to right, ionization energy generally increases. That's because the number of protons in the nucleus increases, so there's a stronger pull on those electrons, making them harder to rip away.
And if you go down a group, what happens then?
Then the ionization energy generally decreases. That's because those outer electrons are further from the nucleus and shielded by the inner electrons. So the pull from the nucleus is weaker, making those electrons easier to remove.
What about electron affinity? That sounds like the opposite, like how much an atom wants to gain an electron, right?
Yeah, you could think about it that way. Electron affinity is the energy change that happens when a neutral atom in its gas phase gains an electron. As you move across a period, electron affinity generally becomes more negative, meaning more energy is released when an electron is added. And down a group, it generally becomes less negative.
And finally, atomic radius.
Yeah.
That's just the size of the atom, right? What trends do we see with that?
Yeah, so across a period, atomic radius generally decreases. Even though you're adding more electrons, you're also adding more protons to the nucleus, which pulls all the electrons in closer, making the atom smaller. But as you move down a group, the atomic radius increases because you're adding whole new energy levels of electrons, which makes the atom bigger.
So all these trends, ionization energy, electron affinity, atomic radius, they all depend on the arrangement of electrons and how strong the pull is from the nucleus. It's all connected.
Totally. And these trends are what make the periodic table so useful. Just by looking at where an element is on the table, you can predict a lot about how it will behave.
It's amazing how much information is packed into that table.
Mm.
So we've covered the structure of atoms and how their electrons determine their properties. But like, how did these atoms actually come together to form, stuff, everything that we see and touch? That's where bonding comes in, right?
Exactly. Atoms are kind of like social creatures. They like to form bonds with each other. And by doing that, they achieve a more stable electron configuration. They want to have a full outer shell of electrons, like the noble gases. Those are the elements that are like super stable and don't react much.
And the two main types of bonds are ionic and covalent.
Right.
What's the main difference between them?
In ionic bonds, one atom donates an electron to another. This usually happens between a metal and a nonmetal. So you end up with ions, a positively charged cohabitation, and a negatively charged anion, and they are attracted to each other because of their opposite charges, like magnets.
Like table salt, sodium chloride. The sodium gives an electron to the chlorine, they become oppositely charged ions, and then they stick together.
Perfect example. Covalent bonds, on the other hand, are all about sharing electrons, usually between two nonmetals. They share electrons so they can both have a full outer shell.
So instead of one taking and one giving, they're both contributing to a shared pool of electrons, like water, H0, or carbon dioxide, CuRO. Those are covalently bonded.
Yep, those are good examples. And the way atoms are bonded really affects the properties of the substance. Like ionic compounds generally have higher melting and boiling points, and they can conduct electricity when they're melted or dissolved in water. Covalent compounds usually have lower melting and boiling points, and they don't conduct electricity very well.
That makes sense. It takes more energy to break apart those strong ionic bonds. And even within covalent bonds, there's another level of detail, right? Nonpolar and polar covalent bonds. What's the difference there?
It's about how equally those electrons are shared. In a nonpolar covalent bond, the electrons are shared perfectly evenly. This usually happens when the two atoms are the same, like an oxygen gas, ORO. But in a polar covalent bond, the electrons are not shared equally. One atom pulls on them more strongly.
That's because of electronegativity, right? How strongly an atom attracts shared electrons. So the more electronegative atom has a slightly negative charge, and the other atom has a slightly positive charge.
Exactly. That creates what we call a dipole moment, like a little arrow pointing from the positive to the negative end of the bond. And the bigger the difference in electronegativity, the more polar the bond.
So, okay, we've got atoms connecting by either transferring or sharing electrons, forming all sorts of different compounds. But how do we actually draw these bonds? How do we represent what's going on? We use Lewis structures, right?
Yes, Lewis structures are like diagrams that show you how the atoms are bonded and where those lone pairs of valence electrons are. Valence electrons are those in the outermost shell, the ones that participate in bonding.
So you're basically mapping out how those electrons are arranged to make the atoms happy, to give them that stable configuration. Usually they want 8 valence electrons, the octet rule.
Exactly. To draw a Lewis structure, you first count up all the valence electrons in the molecule or ion. Then you connect the atoms with single bonds. Those are the lines you see in the diagrams representing 2 shared electrons. Then you add the rest of the electrons as lone pairs, usually on the outer atoms first, trying to get everyone to have 8 electrons.
And those lines, they can be single bonds, double bonds, even triple bonds, depending on how many electrons are being shared.
Right, and sometimes you can't represent a molecule accurately with just one Lewis structure. That's where resonance comes in. Resonance means there are multiple valid Lewis structures that describe a molecule. The real structure is like a blend of all of them, like it's switching between them really fast.
And then there's the idea of formal charge, which helps you figure out which Lewis structure is the most likely one. You want to have the lowest charges on the atoms.
Right, formal charge is a way to assess the electron distribution and figure out which structure is the most stable. It's like a bookkeeping system for the electrons.
So Lewis structures give us this flat 2D picture of how the atoms are connected. But in reality, molecules are 3D, right? And their shape really matters. That's where VSEPR theory comes in, valence shell electron pair repulsion.
Yeah. The SEPR, it's all about how those electron pairs around a central atom arrange themselves in space. They want to get as far away from each other as possible because they're all negatively charged and like charges repel.
So they're like pushing each other away, those electron pairs. And the overall 3D shape of the molecule, that's called the molecular geometry, right? And that depends on how many electron pairs there are and whether they're bonding pairs connected to another atom or lone pairs just hanging out on the central atom.
Right. So the number of electron domains, that's the total number of bonding and lone pairs, that determines the electron geometry. Then the molecular geometry is just the arrangement of the atoms themselves. Like if you have 4 electron domains, the electron geometry is tetrahedral. But if one of those is a lone pair and the other 3 are bonding pairs, the atoms form a trigonal pyramidal shape, like in ammonia. Or if there are 2 lone pairs and 2 bonding pairs, you get a bent shape, like in water.
Ah, so those lone pairs really matter. Even though they're not actually another atom, they push on the other pairs and affect the bond angles.
Exactly. They're like little invisible balloons taking up space. And that means the bond angles aren't always what you'd expect. Like the ideal tetrahedral angle is 109.5 degrees, but in ammonia it's closer to 107 degrees, and in water it's even smaller, around 104.5 degrees.
So we see these common shapes like linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and they all have specific bond angles. VSP is really helpful for visualizing those 3D shapes.
It definitely is. And that 3D shape is really important for understanding molecular polarity, whether a molecule have a positive and negative end.
Right, like some molecules are polar, they have a plus side and a minus side. Others are nonpolar, their charge is evenly distributed. What makes a difference?
Molecular polarity depends on 2 things: the polarity of the individual bonds and the overall shape of the molecule. If there's a big difference in electronegativity between 2 atoms, then that bond will be polar, like we talked about. It'll have that dipole moment.
But even if a molecule has polar bonds, doesn't necessarily mean the whole molecule is polar.
Right, the shape matters. If the molecules are very symmetrical, those dipole moments from the bonds can cancel each other out, and the molecule will be nonpolar overall, like carbon dioxide, co-arrow. The carbon-oxygen bonds are polar, but the molecule is linear, so those dipoles point in opposite directions and cancel out. But water, it has polar oxygen-hydrogen bonds, and it's bent, so those dipole moments don't cancel. Water is polar.
And those lone pairs can mess things up too, right? They often make a molecule polar.
Yeah, they do. Those lone pairs, they affect the electron distribution and can make it asymmetrical, leading to a polar molecule. So it's really a combination of bond polarity and molecular shape that determines the overall polarity.
So we've talked about how atoms connect to each other. But what about the forces between molecules? That's intermolecular forces, right?
Yeah, intermolecular forces, or IMFs. These are weaker than the bonds that hold atoms together within a molecule, but they're still super important for a lot of properties like boiling point, melting point, viscosity, and solubility.
And there are three main types, right? London dispersion forces, dipole interactions, and hydrogen bonding. Can you explain those?
Sure, London dispersion forces are the weakest. They're present in all molecules, even nonpolar ones. They happen because the electrons in a molecule are constantly moving, and that can create temporary dipoles. These temporary dipoles can then induce dipoles in neighboring molecules, causing them to attract each other.
So like a fleeting attraction. And the larger the molecule, the stronger those London dispersion forces, right?
Yeah, the more electrons a molecule has, the stronger the London dispersion forces. Dipole interactions, they're stronger than London dispersion forces, and they only happen between polar molecules. Because polar molecules have those permanent dipoles, the positive end of one molecule is attracted to the negative end of another.
And then the strongest type is hydrogen bonding, right? That's
Yeah.
a special kind of dipole interaction.
Yeah, hydrogen bonding happens when a hydrogen atom is bonded to a very electronegative atom, like fluorine, oxygen, or nitrogen. And then that hydrogen is attracted to another fluorine, oxygen, or nitrogen on a nearby molecule that has a lone pair of electrons.
Like in water. That's why water has such a high boiling point for such a small molecule, right? Those hydrogen bonds are strong.
Exactly. So all these intermolecular forces, they determine a lot of the macroscopic properties we see. Like a stronger IMFs mean a higher boiling point because it takes more energy to break those attractions. They also affect viscosity, how easily a liquid flows.
And solubility too, right? Like dissolves, like
Polar.
polar things dissolve in polar things because they can form those dipole interactions in hydrogen bonds. And nonpolar things dissolve in nonpolar things because of those London dispersion forces.
Right. It all comes down to how well the molecules can interact with each other.
Wow, this has been a really amazing journey. We've gone from those basic subatomic particles to the complex ways they interact and form everything around us. It really makes you appreciate all the intricate stuff that's going on at the atomic level.
It does. And as we've seen, it all comes back to those electrons. They're the key players in determining how atoms behave and interact.
It's incredible how these tiny particles are responsible for, like, the whole universe. As you go about your day now, think about, like, a glass of water, the air you're breathing, anything really. And imagine those atoms and molecules interacting, all those forces at play. It's a whole new way of looking at things.
It is. And the amazing thing is, even tiny differences in how those electrons are arranged can have huge effects on the properties of matter.
It's like the tiniest change can make a world of difference. So that brings us to the end of our deep dive. We've explored the atom, from its basic structure to the forces that shape our world. And now, a little something to ponder. Think about all the amazing materials and reactions that make life possible. They all come down to those tiny atoms and their interactions. What everyday phenomena will you now view through this new atomic lens? That's something to think about.